RISC-V is becoming much more important in the automotive space because it provides a way to customize the design for developers. So, Samir, could you tell us a little bit about how RISC-V and MIPS are working together?
Oh yeah, absolutely. Look, exactly what you said, right? RISC-V is about getting control back into the people who are making systems and developing these systems. So the RISC-V consortium has helped create a very vibrant and standardized instruction set, and it's becoming a very rich instruction set, right? Starting to cover applications which are beyond simple embedded stuff, going into the user space in a pretty material way. And how we are collaborating, how we're leveraging is it's a two-way street, right? We obviously leverage the open source aspect of the instruction set, but we also are starting to contribute back into the community in a pretty material way. Some of our team members are leading very specific segments of the RISC-V thing. Like Robert on our team is leading up the debug and trace, which just got accepted and brought into the community. So that's there. We've started upstreaming now that P8700 is GA and it's available. We're starting to upstream Linux patches on that as well, which has been accepted by that community. So it takes time, but honestly, if you just draw a straight line through where we are to where both RISC-V and MIPS will be, I think we're starting to truly cater to the developer community in a way where they can start building products with that.
Now, a lot of people are designing RISC-V cores and selling them, but one of the challenges in the automotive space is functional safety. Could you talk a little bit about how MIPS is supporting that with the P8700?
Yeah, absolutely. So the P8700 came about as a collaborative project with Mobileye. So right off the bat, we knew we needed to create the product with a functional safety mindset. And that is truly the only way to do something which is functional safety in automotive or even in certain industrial use cases. Retrofitting functional safety on an existing design is very, very difficult. Between all the traceability, between all the steps you have to follow to be able to fulfill the standard. So I think the first and foremost is when you conceive the project, you have to decide whether you're functional safety or you're not. And if you're functional safety, it follows its own complete paradigm of development. It also is more expensive, right? You add more cost to the product, you add more cost to the development, you add more cycle time to the development. But if you're willing to go do that, I think you create something which I mean differentiates MIPS, because I think as best as I know, we are the only ones right now who have this complexity available in functional safety. But for some of these automotive or automation-oriented markets, think about it, right? People are obviously AI is AI, and everyone's on the inference bandwagon right now. But if you're trying to truly bring inference down to things which we interact with on a daily basis, they're all functional safety use cases. So trying to do AI without functional safety isn't going to get you where I think these robotic use cases or autonomous vehicle use cases are going to work. So to us, functional safety is almost as important as just functionality in the code. They are one and the same thing for us.
Now, functionality in the core is also going to be important because of performance, and MIPS provides an out-of-order multi-threading. Could you tell us how that works and how it's incorporated into the standard instruction set that that RISC-V provides?
Yeah, so see, we're obviously using the RISC-V instruction set. So the top level architecture is RISC-V, but the microarchitecture of the core is still very MIPS. That's why I like to call it a very MIPSy core. So still simultaneous multi-threading, still cache coherent, still has the unique architectural elements which made MIPS a very, very strong data processor. So the role of the CPU is also evolving, right? There was a time when the CPU used to be the only number crunching machine. Today, in most cases, when we're catering to an AI use case, there's going to be an AI accelerator or there's going to be a GPU or something like that. So the role of the CPU is also shifting from being the sole number cruncher to someone who's actually more focused on making sure that the biggest number cruncher on the board isn't sitting idle. So the data movement aspect of it, the keeping that flowing and catering to that becomes very key. So as we conceive the P8700, the raw spec and score and the classic CPU benchmarks are important,
Mm-hmm.
and we're very happy with what we have there. But equally important becomes the capability of plugging into the customer's AI accelerators, and catering to that by feeding it, and moving data and streaming it into that. So I think those aspects of the microarchitecture play a very key role in how this has been conceived.
Now, for a lot of automotive applications, a single core is usually not sufficient. You have a multi-core, multi-cluster architecture, and that also lends itself to AI acceleration. Could you talk about how that's built up and how a designer incorporates that into their design?
Yeah, so what we're releasing from MIPS is, you have a lot of flexibility, right? You're absolutely correct. I don't think so anyone's looking for a single core anymore. So I think we are releasing, we have our own cache coherency bus as well, which works very well with multiple of our CPUs. You can configure them as 2, 4, 8, 16. You can have multiple clusters. We are starting to work on cluster-to-cluster coherency as well. Honestly, today's SoCs have become so complex that the days of anyone showing up with a fancy core and saying, "Here you go, and God bless you," I think that we're past that stage, right? I think we're looking at the problem as a more subsystem-oriented problem. So saying if the role of that subsystem is X, how do we go fulfill that? The beauty about MIPS is we also don't have only one core. One core is what we've announced, but we have, as we engage with customers forward-looking, we also have multiple cores, right? We have the out-of-order core. We've also announced the in-order core. We have a few other things in work, and we'll release them over time. But it's a lot about what application we're trying to go meet. And the processing requirements of those applications sometimes tend to be more heterogeneous than homogeneous. And how do we go leverage the assets inside MIPS to solve that is what we're looking at. So the customer engaging with MIPS is not coming in and getting a core. I think they're getting more of a subsystem, and a subsystem which we prove out internally all the way to a GDS. So they're not having to do a lot of that gap filling themselves.
Well, very good. Well, thank you very much for filling us in on MIPS' latest multi-core architecture.
No, absolutely. Thank you.